Enhanced meta-label correction for coping with label corruption. The problem of learning with noisy labels refers to the problem of learning from datasets with corrupted labels. The LNL problem is challenging as the correctly annotated samples are not known a priori. However, the LNL problem has many applications, since in many cases large noisy labeled datasets can be obtained easily. A good example would be crawling online websites and social networks. LNL is interesting also beyond classification. Image segmentation and object detection inherently suffer from noisy labels. By observing large noise-labeled data pairs X and Y tilde, and some calibration set we wish to minimize the true error, namely the expected risk with respect to the true label distribution. This is challenging as the noisy label may depend on the instance X. An implication of this is that harder images would be more frequently mislabeled. In traditional supervised learning we minimize the average loss of the data. Usually, our models model the conditional distribution of Y given X. However, in our case the ground truth labels are corrupted. The idea would be to replace them with a teacher model, Q alpha, which models Y given X and Y tilde. For every realization of alpha, the main model, the student, solves a different optimization problem. But the question is, how do we optimize the teacher? The answer would be to use the feedback from the optimized student on the calibration set. This naturally leads to a bi-level optimization problem. These are essentially the main ideas of prior work MLC. However, there were multiple problems with MLC. Their optimization scheme was very slow and inexact. This led them to a suboptimal design of the teacher. Our contribution is threefold. We revisit the optimization process by simplifying the Hessians that appear there. We exploit this and derive a fast and precise algorithm for computing the metagradients. Furthermore, we present an improved teacher architecture as well as a new teacher training objective. In a bi-level optimization problem, each realization of the outer parameters defines a new inner problem. To solve such problems we iteratively update W for a fixed value of alpha to approximate W star. After multiple iterations we update alpha as well. In order to apply first-order methods we need to compute the feedback loss gradient with respect to alpha. The first term of the gradient can be easily estimated with backpropagation. However, computing the second term is the interesting part. We propose to estimate W star using k-steps of gradient descent. Note that it's possible to differentiate through the GD updates. This leads to both single and multi-step strategies for computing the metagradient. The problem is that both strategies require computing mixed Hessians of the inner level problem which is intractable in a straightforward fashion. Our idea was that when we consider each sample separately, it is possible to express the Hessian of the CE loss as a product of Jacobians. The proof idea is that the CE loss can be expressed as an inner product between a function that depends solely on W, and a function that depends solely on alpha. This allows us to nicely re-express the metagradients. Exploiting these forms, we derive the FPMG algorithm to compute the metagradients. FPMG utilizes efficient Jacobian vector product and vector Jacobian product to efficiently compute the metagradients. Theoretically, FPMG is at most 3 times slower than a regular backprop and can be easily batchified. Our second contribution is an improved teacher architecture. MLC's teacher architecture uses student-generated features. This leads to a strong student entanglement and to a high confirmation bias. Our teacher architecture has its own feature extractor and predictor, and is able to incorporate the prediction with the noisy label signal. The teacher learns to incorporate both signals and is completely disentangled from the student. Our third contribution is a novel teacher training objective. The idea is as follows. Given a batch of clean samples from the calibration set, we split it to halves. For the first half we set Y tilde to be the original label, and for the second half we insert noisy labels. We encourage the gating mechanism to predict whether Y tilde is clean. We train the gating mechanism using the binary CE loss. While noise injection and detection is a well-known technique for noise robustification, we propose a new noise injection method. The trivial injection method is random. We propose an adversarial noise injection technique. We use the teacher's classifier to get a prediction Y hat. If the prediction is wrong, use it as the noisy label. Otherwise, use the second probable class. All in all, the teacher's objective is composed of 3 terms, the meta loss, the noise detection BCE loss, and a regular supervised training objective on the clean calibration set. On the CIFAR datasets, we adopt the standard evaluation protocol, in which noisy labels are synthetically inserted. eMLC achieves state-of-the-art results on all of the settings. As can be observed, sometimes the single-step strategy is preferred, and sometimes the multi-step strategy works better. The real-world challenging dataset Clothing 1M is a dataset of confusing clothing items scraped from the web. The mistakes in this dataset are human mistakes, and therefore hard to tackle. On this dataset, eMLC suppresses prior art by 1.5%, and MLC by 3.5%. We now discuss the effectiveness of our meta-learning procedure. As can be observed, eMLC suggests an improved convergence of the meta-objective, both in terms of speed of convergence and stability. On the same hardware, single training epoch takes half the time compared to MLC, with significantly more meta-parameters.